Dear students, welcome back to another video session on coupled circuits. So before getting into the topic, let us revise some of the basics regarding coupled circuits. Current and flux in a coil. Whenever a current flows through a conductor or a coil, a magnetic flux will be produced around the conductor. Magnetic flux is the magnetic lines of force present around a permanent magnet or an electromagnet. Now the direction of flux lines around the conductor will be identified by using right hand rule. So consider you are holding a current carrying conductor such that your thumb is pointing towards the direction of current. Here assume that the current is flowing in upward direction. So your thumb is pointing towards the current. If that is the case, then the flux produced around this coil will be, the direction of flux produced around the coil will be like the direction in which the other four fingers are folded. That is all the remaining four fingers are folded in this direction. Hence the flux produced around this conductor will also be in this direction. Now let us discuss about Faraday's law of electromagnetic induction. So whenever a conductor or a coil links with a magnetic field, an EMF or voltage is induced in that conductor. You consider this is a conductor or a coil having some 6 or 7 number of turns wound over a core, and it has two terminals which are connected across voltmeter for measuring the voltage, voltmeter or galvanometer. And this is a permanent magnet having north and south pole. So you can see that when the magnet is going in or coming out, there is a voltage induced across the coil. So this is what Faraday's law of electromagnetic induction. The flux is linking with the coil, and hence EMF is induced across the coil. You can see that when the magnet goes in, there is a positive voltage. When the magnet comes out, there is a negative voltage. When the magnet is stationary, there is no flux linking with the coil, and hence the voltage will be zero. Now the voltage induced, the magnitude of the voltage induced is proportional to the number of turns in the coil. More the number of turns, more will be the voltage, and the speed at which the coil or flux moves. If the magnet is moving in and out fast, then the voltage induced also will be high. Therefore it can be written as an equation that the induced voltage V is equal to N into d phi by dt, where N is the number of turns in the coil and d phi by dt is the rate of change of flux, how fast the flux is linking with the coil. That is what d phi by dt. So please remember this formula, V is equal to N into d phi by dt. Let us discuss about self-inductance and mutual inductance. So consider a coil with n number of turns and a current of I ampere is flowing through it. Definitely it will produce a flux of 5 Webers. This is the symbol used for representing the flux, whose unit is Webers. As per Faraday's law, this is the coil which is carrying a current of I ampere that produces a flux of 5 Webers. So there will be a voltage induced across the coil as per Faraday's law, that is V is equal to N into d phi by dt. So flux phi is produced by this current, and hence any change in phi is because of this change in current. Therefore you can write this d phi as d phi by di and di by dt. So both are same. And here this N into phi by I is equal to inductance L. The inductance L of the inductor is N into d phi by di. So this is called the self inductance of this coil. Self inductance of the coil, where L is equal to N into phi by I. Next one is mutual inductance. We need two coils with self inductance L1 and L2 being kept close together to understand the concept of mutual inductance. So assume that two inductors are kept in close proximity. They are having self inductances of L1 and L2 respectively, and a current is passed through one of the coils. Coil 1 is having N1 number of turns and coil 2 is having N2 number of turns. When you pass a current through this coil, it creates a flux of phi 1. The total flux produced in this coil is phi 1. This total flux phi 1 has two components. One is phi 11 that links with coil 1 only. So some of the flux will be linking only with this coil, and some of the flux will be linking with both the coils. So the flux that links only with the first coil, I am calling it as phi 11. See here, this is phi 11, and phi 12 links with both the coils. See, you can see the notation. The one represents the flux produced by coil number 1, and 2 represents it is linking with the second coil also. So here you can call it as phi 12. Therefore the total flux is sum of these two. So even though both are physically separated, there is no direct link between these two coils. They are magnetically coupled. The total flux will be phi 11 plus phi 12. You assume the same two coils. Now let us see the voltage induced in coil 1. As per Faraday's law, it is N into d phi by dt. Since it is coil 1, we write it as V1, and number of turns in coil 1 into d phi 1, that is flux produced by the coil 1. And this can be written as the change in flux is caused by current, therefore d phi 1 by di1 into di1 by dt, both are same, where this is the self inductance L1 of the coil 1. Now voltage induced in coil 2. Here the flux produced by the coil 1 is linking the second coil also, therefore as per Faraday's law there will be voltage induced in second coil as well, which is given by the number of turns in the second coil. And what is the flux linking with this coil? Phi 12. So d phi 12 by dt, and this can be written as the change in phi 12 is caused by I1. Therefore d phi 12 by di1 into di1 by dt. Any change in current I1 will cause a change in phi 12. Therefore this depends on this current I1. So here this is called mutual inductance M. So M is equal to N2 into d phi 12 by di1. So mutual inductance is also same as normal inductance, whose unit is henries, but it is because of the flux produced by one coil linking with the other coil, where M is the mutual inductance between the coils. Similarly, you can consider a current I2 passed through the second coil, and there will be self inductance and mutual inductance, self voltage, mutual voltage, all these things will be there as per the previous case. You can just go through it. everything, all the equations are similar to the uh, first coil. Again here the voltage induced the first coil is because of this flux 5 to 1, that is because of this mutual inductance. Now let us see the definition for mutual inductance. It is the ability of one inductor to induce a voltage across the neighboring inductor. So when you have two coils coupled together, so the flux produced by one coil will be linking with the nearby coil, and hence there is a voltage induced. So this ability is called mutual inductance. So it is also measured in henries. So when you have two coils and voltage is induced across each coil, then we must understand which terminal of that coil is positive and which is negative. So this is identified by using dot convention, for which a dot is placed at one end of each coupled coil to indicate the direction of flux and current. So like this is a mutually coupled coil where there is a dot placed here. So based on the current entering whether in the undotted terminal or on the dotted terminal, we can find the voltage induced in the nearby coil. Thank you.